Today we will study about the deflection due to bending, how to calculate the deflection caused by bending. And last class we studied about how to calculate bending stress which occurs in beam. And today we will study about the deflection. Okay? Beam when subject to an external load, and the beam will deflect. So this is the most important part in the whole solid mechanics. And it is quite different from other subjects like torsions and any other structure. Any other structure do not have any deflection, but in beam, deflection is very important. So in this chapter will be second to last one. After this chapter 12, we will have buckling, and buckling we will just review what the concept of the buckling. But actually, this chapter 12 is the last chapter of this course. Anyhow, this chapter we will study about introduction to the deflection due to a bending, and moment curvature relationship, and Gaboni equation, and boundary condition, and solving related problem. And I will introduce a little bit about strain energy. Okay, here is our problem statement. Problem statement means that what kind of a problem are we going to solve? Well, this is the beam, and this beam are subject to many different types of the vertical load, including concentrate bending moment and concentrate vertical load. Of course, we could have a distributed load which is a function of x. And this beam is also has two boundary conditions at two ends. Here, left-hand side and right-hand side, we should have a certain boundary condition. And the question is that how much deflection we will have. Okay? The deflection that will be unknown to solve. So here, given cross-section and material properties of a beam, cross-section and material properties. Cross-section means basically a moment of inertia, and material properties is the Young's modulus. And second given condition is the external load as a function of x, and boundary condition at both ends. Okay, keep that in mind. We have a three condition which need to be specified, and then here is what to find. First, a vertical deflection Vx as a function of x, y directional or vertical directional deflection as a function of x. And once we have deflections, we can always calculate the moment distributions. Calculation of once we have a moment, we can calculate the bending stress. You know, the sigma is given in terms of a bending moment. So once we have the bending moment, we will be able to calculate the bending stress. And then also we can calculate the shear force, which enable us to calculate the shear stress. So keep that in mind. We will calculate the vertical deflection and bending moment and shear force. Bending moment will give us the bending stress, and shear force will give us a shear stress. And those two, bending stress and shear stress, we already studied last chapter, right? So basically here in this chapter we will learn how to calculate vertical deflections. Okay. And in this chapter, we need to pay attention to statically indeterminate problem. What is a statically indeterminate problem? Well, we cannot calculate reaction force by considering only statical equilibrium equations. We have a more unknown than equilibrium equations. For instance, we have clamped, and here is the simple support, and so we have vertical force and bending moment, and here is the vertical force. How many unknown do we have? How many unknown do we have? We have 3 unknowns, right? And how many equilibrium equation can we use? 2. 2 means vertical equilibrium equation and moment equilibrium. Remember those 2 differential equation, right? Those 2 differential equation. So anyhow, this problem is a statically indeterminate problem. Whereas this one is a statically determinate, we only have 2 unknowns, which is this vertical force and bending moment. Those are 2 unknowns, and 2 equilibrium. So this is a statically determinate. Okay, and this is the 3 unknowns and 2 equation. So statically indeterminate. So this one, both of them apply to this case. Anyhow, for this statically indeterminate problem, well, actually this kind of statically indeterminate problem quite more general than statically determinate. So how can we solve this kind of statically indeterminate problem? Well, we should be able to solve this one, but how? Now, here is the answer. We have to consider deflection. Okay? Here we consider only equilibrium equation, and we couldn't solve the problem, reaction force, but in statically indeterminate, in addition to equilibrium equation, we will use deflection, and then we are able to calculate all the reactions, which are number of which is more than equilibrium equation. So how to drive this Gaboni equations for deflection? Here we need to, this is a moment curvature relations. Okay, moment curvature relation is new here. And last time we learned about the relation between moment equal EI curvature, right? Moment equal EI curvature. And curvature is given as the rate of rotation, right? Rate of rotation. At the end, cross section is rotating. Okay. So this is the relation between moment and curvature. And curvature is the relation relating deformations. And theta is given here. And theta is changing along with x. The rate of this x, theta with respect to x, is the curvature. And here is the new relations. Okay, here is the new relations. This theta, well, this theta is simply tangent theta is the slope of this deflection, right? This is the Vx, and if this is the slope, and tangent theta is simply dv dx, right? Now, here is the key part. Tangent theta approximate theta. Why? Small deflections. Okay, small deflections. For large deflection, we cannot say this, but we are considering only small deflection, so tangent theta will be just theta. Okay, this is a key part. So this d theta dx, and theta is given as this one, and if we put it here, then the curvature will be dv dx twice derivative, right? Twice. This is the core part in this chapter. Other than that, they are all same equations. You know, these moment curvature relations and the equilibrium equation, which I will show you later. They are nothing new. But this is the new relations. Curvature is given as d theta dx, and then this theta is derivative of deflection. So this is the relations. Small deformation, we have the moment x equal ei, second derivative of v with respect to x. Okay? This is the moment curvature relation. Very important relations. In other words, if we have a beam subject to a moment, constant moment, then this beam will have, surely this beam will curve, and these equations, as you can see here, we will have, if let's say this is the moment is constant, then V is simply second order deflections, A and B and C, right? Because it's a second derivative is given as the moment. If a moment is a constant, then deflection will be a function of second order function of the x, right? So anyhow, this is the relation we're going to use. Keep that in mind. And now back to our equilibrium equation. Those are two equilibrium equations which we already derived using from vertical deflection, vertical equilibrium and moment equilibrium. Which one was the vertical equilibrium? This or that? the second equation is the vertical equilibrium, right? You remember here we has the V plus dV, and here is the V, and we had Q, so all the y directional force, and this disappear, and so Q dx plus dV should be 0. So we got this equation, right? So whenever you see this equation, you need to understand this procedure at the same time. Okay, so y directional force equilibrium. And this one, where we have the moment plus dm and moment like that, and we have some, upward equilibrium, and then we have V here and V here. Actually, we have dV, but dV doesn't contribute to this term. So anyhow, VV is causing moment, right? V times dx. And V times, well, this m and m disappear. So V times dx should be same as incremental moment. So that relation gives us this. Okay? So again, moment can have some increment. That incremental moment was caused by those two shear force. So V dx should be same as dm, right? dm, V times dx is same as dm. So this equation means this equation is from this one. So you need to understand this, and you need to understand that. And these two equations are equilibrium equations. Now, if we combining these two equilibrium equations, or eliminating this V here, and this V, we put it here, then we can have this equation, right? So moment is given in terms of, not given, it is a differential equation is given second derivative of moment, and Qx is a function of x, right? So whenever we have the Qx is a function of x, then we can integrate twice, and we get the m. And during integrations, we have a two integration constant. Those two constants should be determined from boundary conditions. But this procedure is only for statically determinate problem. But now we are trying to solve the statically indeterminate. So combining these and previous these relations, okay, let's combine them, put it here. Then we have, this is the m, we have this fourth order differential equation. Fourth order differential equation. And if EI is a constant, then EI can come out of these differential equations, and you got this. Okay? So this is the final equation. This is the final equation. And so from here, this is the last core equation in this beam theory. And you should be able to solve this differential equation to determine deflection and bending moment and shear force. See, how many? The order is a fourth order. Means that when we integrate, this equation is Qx is given. So when we integrate, how many integration constant will we have? 4 constant, right? We have a fourth order. So integrate one time, we got the one constant, and second time, second constant, and so on. So V will be given in terms of x, but there will be 4 extra constant which you should determine. But from where? Boundary conditions. So how many boundary conditions do we need to use? 4 boundary conditions, okay? Keep that in mind. 4 boundary conditions. Always 4 boundary conditions. Okay, again, you have to keep that in mind. How did we drive this equation? First, moment and curvature relation, and curvature is a function of deflection. Okay, combining them, moment equal EI V second derivative, right? That's the one equation. And 2 equilibrium equation give us moment second derivative given in terms of a QX. This from equilibrium equation. And combining this one and that moment curvature relation, we will end up with this Gaboni equation. And this is a differential equation. Is there anybody who didn't take any differential equation? So you should be able to solve this differential equation. This is a very easy one. All you need to do is just integrate. Integrate left and right hand side. Okay? Step by step. That's all. Now, okay, once we have this one, means that we need to have 4 boundary conditions together with this equation. With 4 boundary conditions, we will have a V. Now, once we have a V, look at this. Look at the previous one. Second derivative. Once you have a V and you have a second derivative and you get moment, right? So once you have V, you second derivative again and you multiply EI, this will be what? This will be moment, right? And do it again because we have a relations. We pay attention to here. We have, if we derivative one more time, m with respect to x, then you get the v, right? So that means from this equation, EI v 1, 2, 3 minus will be v. Okay, you got the procedure. You have a differential equation together with the boundary conditions, and you have a v. Solving this one, you get the v, and second derivative of v will give us the moment, and the third derivative will give us the v. So all function of x. Okay, I will give you a chance. Open your blank pages. Open your blank paper and write down what you just learned. You need to keep practicing. Don't discuss, okay? You just write down what I telling you, okay? At the top, write down your name and write down moment. Don't look at me. Look at your paper. Write down the relation between moment and curvature. And second, write down the relation between curvature and deflection. K is given second derivative of deflection V. Third, write down equilibrium equation, vertical direction. Relation between curvature and deflection. And third one is the equilibrium equation in vertical direction. And fourth, equilibrium equation, moment equilibrium equation. Moment and V, right? Next, equilibrium equation M in terms of Q. Okay, M equal EI curvature, right? M equal to EI curvature. Close your eyes and try to remember. And you have to keep practicing, and you have to keep writing. So moment is given EI curvature. And what is curvature? Curvature is given d theta dx, and theta is the first derivative of V. So second derivative of V, right, which is K, right? So moment is EI second derivative of V with respect to X, right? Now, what's the next one? Now we need to consider equilibrium. Yes? Y-directional equilibrium equation, what is that? dV dx plus Q equal 0. And what is the moment equilibrium equation? dm dx plus V equal 0. Okay, if we combine those two equilibrium equations, we are eliminating V. And what do we have? Second derivative of moment, right? Second derivative of moment will be equal to what? Qx, right? Qx. Now, instead of that M, what do we have? Moment equal EI V second derivative, right? Okay, put it there. Then we have EI is a constant. Then EI V, how many derivative? 4 times equal to Q. Okay? So there are 4 or 5 steps to reach this final equilibrium equation. These are a key procedure. Okay? A key procedure. And now you will see how powerful this equation will be. You can solve any kinds of statically indeterminate problem. Now, for instance, this one. We had clamped and we had a simple support, and we applied a P, any load. We couldn't solve this one, right? We couldn't solve. But now, if we use that equation, then we can solve this one. Jangbong, you pay attention here. So how many boundary conditions do we need? 4 boundary conditions to solve that 4th order differential equation, right? So let's find out what kind of a boundary condition we can have. That's the key part. Well, again, we went through all the procedure to reach this differential equation, and now next step is how to make use of those 4 boundary conditions. So boundary condition will be one of the key part. Okay, so as he said, 4 boundary conditions are needed. And here is the governing equations, and Qx, first of all, Qx is given as a function of x from 0 to L, and we need to have 4 boundary conditions. Well, first of all, what kind of a Qx can we have? Well, here, for instance, uniform Qx. Then Qx will be minus Q0, constant. There is why there is a minus there? This is a downward, right? Well, usually the upward is a positive, so downward will be minus. Now, second case, if the Qx is the linearly varying like that, then you have x over L Q0, meaning if x equals 0, starting with 0, and if x equals L, there will be Q0, right? And so it's a linearly varying, and this is the all upward. That's why we have a positive. Now, if this one a little different, a little more general, well, you can certainly have these equations, x over L Q0 plus Q0. This is just one example. We can combine this one and that, and we can simply get this one. Now, here is the key part. This kind of a continuous distribution is easy. But how about this kind of a discontinuous distributions and concentrate load and concentrate moment? How are we going to handle this kind of a Qx? Well, this Q it can be simply says 0 for x if x is less than L over 2. And if x is greater than L over 2, then Q is simply Q0. Okay? Is that right? So you should be able to write down this equation. And there is a special symbol which indicates this discontinuous function. It's called singularity function, and x minus L over 2, where singularity function, if singularity inside is a negative, then we just treat them as a 0. If it is a positive, then this parenthesis just become regular parenthesis. So you will see what it means from these definitions. And for the concentrate load, do you remember that there was a section called singularity function? We just skipped, and we will go back that section and study about this singularity function, okay? So anyhow, this P is a concentrated load, and this Qx can be written to represent this P like that. Pay attention here, there's a minus 1. And concentrated moment, we write down minus 2. Well, we will study more about the singularity function, but most importantly, this Q needs to be given in terms of x. Now, boundary conditions. We need to have 4 boundary condition to solve differential equation. And what kind of boundary condition do we have? We need to understand. Okay, for instance, clamped. Well, this is very typical boundary condition. In the clamped, what are given here? What kind of conditions are given? Given condition is simply there's no deflection and no slope. V prime is the angle, right? Slope. So V and V prime should be 0 at the clamped. So how many conditions do we have? We have 2 boundary conditions for these clamped conditions. Now, okay, again, this is the key part. Simply support. Simply support. What are the conditions? Simple support. There is no deflection, right? No deflection. So V is simply 0. And what else? What else condition do we have? So moment equals 0, right? Moment equals 0. Moment is given in terms of V prime. Am I right? Moment equal EI V double prime. Remember this equation? Right? If moment is given, that means double prime second derivative is given. Okay? Moment is given, that means the second derivative is given. If shear force is given, then third derivative is given. EI V third derivative is V. That's why, as it says here, V is a third derivative of V, EI. So V itself is a deflection, and V prime is the angle of rotation, and double prime is the curvature or moment, right? Moment is EI curvature, and third prime is shear force. Okay? These 4 different types of boundary conditions. And here we have a V prime. And here we have a V and V double prime. You may ask here, oh, how about the V double prime here? V double prime. V double prime. Can we specify V double prime curvature here? Simply not, because the moment is unknown. Okay? Moment is unknown, so curvature is unknown. But known condition is the V and V prime. And here, deflection itself is 0, and moment is given, which is 0. How about the shear force? That's unknown. We cannot specify, right? How about the change of angle, which is unknown? We cannot specify. And here is the free ends. What does free ends means? Free ends means that no shear force, no moment, right? So shear force 0 means third prime is 0. Moment is 0 means that double prime is 0. Right? Well, it's same as the free, except non-zero P0 and moment 0. So as you can see here, any boundary should have at least always 2 conditions. We have a V1, 2, third prime, and either combination. This one, you have a V and V prime, right? This one, simple support, V and double prime, and here free and double prime and third prime, and so on. So each boundary How many boundary conditions? Left-hand side, right-hand side, always 2 here, 2 here. Totally 4. Yeah, let me ask, why do we need a 4 boundary condition? Huh? Why do we need to have a 4 boundary conditions? Yes, there is a 4 integration constant after this integration, right? So it's very much straightforward, very much, you can just follow the procedure. But again, you need to understand how we drive this equation. Once we have equation, now all you need to do is integration this one, and you have a 4 constant, and you get those 4 constant using 4 boundary conditions. Now, let's try to solve a real problem. Now we learn how to, what kind of what is the governing equation and what are the boundary conditions. Let's try to solve real problem like that. Well, how many unknowns? Well, whenever you have this equation, okay, in your final exam, you have to start with writing equilibrium equations. Okay? Otherwise, you're not going to have you will have a minus point. Keep that in mind. Always, you have to write down this equation. Okay? And here, Qx is what? Minus Q0. And what would be the next step? Next step is the boundary conditions. At x equals 0, what kind of boundary condition do we have here? X equals 0. V equals 0. There's no deflection. And what else? V prime equals 0. There is no slope, right? And x equals L. What kind of boundary condition do we have? Yes, V equals 0 and at the simple support, what is the condition for the simple support? Right, moment equals 0, right? Moment means what in terms of a V? V double prime equals 0. So again, you have to write down these equations, okay? That's first one. And this is the second equation you have to write down, and this is the third one you have to write down. 1, 2, 3, you have to write down. You may not solve this equation, but once you write down this one, you will get 50% score, okay? Keep that in mind. If you just miss that, you're not going to have a score or grade. Now, once you write down this one, let's try to solve. How can we solve? Well, integrate equation 1, EIV1 to 3 equal, what is that? Qx is minus Q0, right? So minus Q0 x plus C1. Just one integrate one time, right? What will be the next one? Integrate one more time, EIV second derivative minus what? Q0 x squared over 2 plus C1x plus C2. Yes, that's the second integration. Now, what's the third? One more time, EIV prime equal minus Q0 6 times x3 plus C1x squared plus C2x plus C3. Right? Okay. Now, integrate one more time. EIV equal Q0 x4 and 24 plus and 6C1 x3 plus 2C2 x2 plus 3x plus C4. Well, all you need to do is just integrate Gabor equation 4 times. Okay? Now, what would be the next step? We have to solve C1, 2, 3, 4 using boundary condition. How many boundary conditions do we have? 4. 1, 2, 3, 4. We already have. How many unknowns? We have 4 unknowns in terms of C1, 2, 3, 4. So let's try to solve this one. X equals 0. X equals 0. EIV. X equals 0. 0 means 0, 0, 0, 0 plus C4 needs to be 0, right? So C4 is simply 0. And so I will say this is the A, B, C, D boundary condition. This is the A boundary condition. And B boundary condition, what is that? V prime equals 0 at x equals 0. Where is the V prime? Well, we have a V prime here, right? So EI V prime at x equals 0, x equals 0, then 0 plus 0 plus 0 plus C, 3 equals 0. So we can easily see that C4 and C3 are 0, right? C3 and C4 are all 0. Now using equation C at L, x equals L, V equals 0. So using this one, EIV, x equals L minus 24 Q0 L4 plus 6 C1 L3 to C2 L square equal what? 0. Right? This is a 0. And boundary condition D, we have a EIV double prime at x equal L, and using this one minus Q0 L square plus C1L plus C2 equal what? 0. So from these two equations, what can we get? We can get C1 and C2. Yes. So as you can see here, I'm sure you can solve C1 and C2. And C1 and C2, look at here, look at. This is the function of x force power. The reason is simply this one is the constant. Starting with constant, you integrate 1, 2, 3, 4, you come up with 4 times of a force power of x, right? And you can, if you plot them, deflection will be something like that. You should be able to draw this kind of deflection. Pay attention. See, this one, you cannot say this way, right? This is wrong. Why? Because at here, the deflection should be 0 and angle should be 0, right? Tangent. So it needs to be this way and this way. And here, so simple support means that you should be this way, right? You should have a certain angle. There's a big difference, this one and this one. Clamped and simple support is a big difference. The major difference is the angle. Here is the angle, and here is the angle is 0. Okay? If you are asked to sketch the deflection, you have to have this sketch. In final exam, you will be asked to draw a sketch of deflection. Then you should be able to draw this kind of deflection. Okay? Remember, if we don't know this differential equation and how to solve it, there's no way. I mean, using this is a typical statically indeterminate problem, and this is the procedure of how to get the deflection. Once we have deflection, now let's say we want to calculate the moment distribution. How are we going to get moment distribution? Well, since we know the C1 and C2, this is what? This is the moment function of x. C1 and C2 are already given, right? So this is the moment distribution. The importance of moment distribution is that, can you tell us that where is the maximum moment? Where? Can you tell? Not easy to tell. We don't know. It needs to be calculated from this equation. Okay, this equation. And how about the V? Well, V is the, this one, right? Third derivative is the V. So this needs to be minus Vx. Back a slide, this one, okay? Any question up to here? So we will have a little application of this deflection. We have a 2-beam support here, and we push down, and there could be many different types of questions and problems we can think of, where this is the this kind of a problem can happen in real structure, real design. We have 2 beams, and there is a little contact here, and once we push here, how this beam or this beam will deflect. It's not an easy question, and you should be able to solve this kind of question. Well, instead of distributed load, we have a concentrate load. How can we solve that? Well, we need to use the singularity function. Okay, singularity function, which we will cover next class. And what if we have a two support? 1, 2, 3. Very difficult. So there is some trick and there is a way. So we will learn how to solve that. Okay. Okay. So well, this is the again last chapter, and we will practice many questions about the beam bending.